Saxon Advanced Mathematics. This is a special lesson on chemical mixture problems. Luke, this is for you and anyone else who might find these problems annoying and want a little bit more of a reminder. So put on your white lab coat, put on your splash goggles, and we're going into the lab. We are chemists today, and we've got two specific and different kinds of problems that we need to solve. John calls them type A and type B, so we'll run with that. But I want you to pay close attention to the diagrams and think about what we're doing with these chemicals. So here comes our type A. With type A, we have two bottles of the same chemical that are different strengths. If you've ever looked at a bottle of hydrogen peroxide or like the kind of alcohol you use like in first aid, they have percentages on them and they're not all the same strength, which is the whole gist of what this problem is about. So in this type of problem, we have the same chemical in different strengths. And the way that we measure the strength of it is by percent, just so you know, right? A lot of chemicals that we use are mixed either with water or some sort of like a neutral base. Glycose is one that allows the chemicals to be used without being their full strength, right? At full strength, they would be a little caustic, I think is a scientific word. They'd be too strong. They'd burn our skin. They're not good. So we're trying to use these chemicals that come in certain percentages, and we're trying to create a new strength or percent okay? So we've got, in these types of problems, we have the same chemical in different strengths. We usually have two bottles, one in each hand, right? And what we're trying to do is we're trying to create a new strength or percentage that is between the two that we have. So we're trying to pour a little bit of one and a little bit of the other and have it come out to be something in the middle. I like to call these Goldilocks style problems sometimes because they are, one's too high and one's too low. The way that we draw the picture for these is like this. These are the two chemicals that we're starting with. All right, and then this is the pan we're gonna pour them into. So think of it, you know what beakers, these are beakers and this is like a flatter pan. So this has got one percentage and this has got the other percentage. Let me just look at this problem. We're gonna do 18.5 and I'm gonna use those percentages. Okay, we're trying to find a mixture. It was necessary to mix a quantity of 20% alcohol with 80% alcohol. So this is 20% in this container. And I'll tell you what, these problems don't make me happy unless I draw the water line at the top. And the other beaker has 80%, okay? One's kind of low, one's kind of high. And we're trying to create 56%. Okay, do you see what I mean about the Goldilocks? This one's too low, this one's too high, this is just right. So we're gonna take some of this and pour it in this pan, and we're gonna take some of this and pour it in this pan, and that's how we get this new, right? But how much do we need to pour of each in order to get 56%, right? We can see that 56% is in between these two, but how much exactly do we need to put in there? Okay, that is the whole mystery. And I want to do this first problem before I explain the other kind. Okay, so what we're going to do is we're going to think about the quantities too. These are the strengths, but we also have how much, right? Like gallons or liters. We can measure the amount in each of these containers as well as know how strong it is. So in 18.5, which is our example here, we know that we want to have 1,000 gallons in the end. Okay, and we don't know how much of these other ones we're going to put in. So what we're going to do is we're going to create variables that will stand for the number of gallons. This we're going to call P, and this we're going to call D. Now let me write those down so that you can understand. P equals the amount in gallons of the 20% that is solution that is needed. Okay, so this will be an amount in gallons that will tell us how much of the 20% to use. This D equals the amount in gallons of the 80%. What John does is he uses these letters specifically because P stands for pour and D stands for dump. And he wants you to visualize yourself as, you can be a pharmacist or you can be a mad scientist. John tends to say pharmacist. I like mad scientist. We're pouring these amounts into this. This didn't have anything in it when we started, right? The only liquid that's in this container is what we have poured from the other two. That might be confusing. I'm trying to think of all the different ways this problem could be confusing. And you know, I can think of a lot. So we're taking some of this and we're pouring it in here. We're taking some of this and pouring it in here. And that's where this liquid has come from, right? It's only what we've put in. There was nothing in here at the beginning of the problem. So we're going to write a system of equations that will allow us to figure out how much we poured in and how much we dumped in. Two ways of saying the same thing. John just wants us to have different letters. I think it's kind of a fun, clever way to set up the variables. So we know that that amount is gallons. So we know that the amount that we pour in of the 20% plus the amount that we dump in of the 80% has to equal 1,000 gallons. Okay, so there is what we would consider, if you think of our old coin problems where we always had a quantity and a value, this is like our quantity statement, is it? Because it's just the number of gallons without taking into account how strong the concentration is in that particular part of the liquid. Okay, so we're halfway there. Now what we want to do is take into account these different percentages. So what I'm going to do is I'm going to write a value statement. Just like with our coin problems, we multiply the number of coins times how much they're worth. We're going to multiply the amount that we pour in by the strength of it. So I'm going to use decimals because 20% equals 0.20. So 0.20 times the amount that we pour in plus 0.80 times the amount we dump in will equal 56.56 times the amount that we have in there. Do you see how there's the P, there's the D, and there's the 1,000. What we've done is we've taken this original statement and we've multiplied it by the percentage associated with that part of the problem, right? Pouring is the 20%, dumping is the 80%, there it is, and the 1,000 that we get in the end is at 56%. So we take this original quantity statement and we multiply it by each of the percentages. Now, because I don't want these evil decimals in my cute little problem, I'm going to, in effect, multiply each term by 100, and that will bump the decimals out. So I'll have 20p plus 80d equals 56 times 1,000. All right, so I just brump, 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 brump. Okay, now I'm gonna lightly squiggle through this one because I don't want to use him anymore. I will now recognize that I have a lovely little system of equation that needs to be solved here. Haven't multiplied that out yet, but I will very soon. Now, how should we solve it? Should we eliminate or substitute? Well, we could do it either way. What I'm going to choose to do is I'm going to rearrange this first one. I'm going to bump the d to the other side. So I'll change this into p equals 1,000 minus d. Right? I just subtracted that. Now I'm going to gently squiggle this out so that I'll remember to look at this. Now I'm going to take this p and substitute this in. So it will be 20 times, not p, but 1,000 minus d, plus 80d equals, and now I'll just multiply this out, 56000. Okay, so we just substituted that in. Now we're ready to distribute. And that will be, wow, that'll be 20,000 minus 20d plus 80d. Sounds like I'm saying ADD, but I said 80d. Beautiful, right? We can combine these two as like terms, and we can subtract 20,000. I feel it coming together. Now we shall get, let's see, that'll be 60d, right? Minus 20 plus 80 equals 36,000. Oh, it's gonna be good, right? I'm gonna flip to my next page and finish the math, and then I'll come back and look at this picture. 60d equals 36,000. Divide both sides by 60, and we get d equals, that goes there, it's going to be 600. Okay, that looks good. Let's take that back to the first page and see what that means. Okay, d equals 600 is our answer. So I'm going to take that right here. Now let's figure out, what does that mean? We said that D is the amount in gallons of the 80% solution needed. Oh, okay, so we can write gallons here, right? So in order to create this new concoction, we're gonna need 600 gallons of this bulb. We still don't know how much of the 20% we need though, but we can figure it out because we see right here, P equals 1,000 minus D. So this is going to have to be equal to 400 gallons, isn't it? I'll just put a single G because I ran out of space, right? So just like many other of our problems, we use one of our original equations, or this isn't even an original, it's a derivation, but we use one of our other equations to solve. So this is my final answer, and I'll write it here. Again, P equals 400 gallons. D equals 600 gallons. We use these variables and this diagram to create our system of equations. Solving it is probably not the challenging part for you. That's probably fairly familiar. That wasn't the trick. The trick is in setting it up. This is how we know to use type A, because we have the same chemical in different strengths, and we're creating a new strength or percentage that is in between the two that we have. And again, I think of these as the Goldilocks problems because this one's too low, this one's too high, This one's just right. Okay, that is the first one. Now, the second one is really the same. And I'll show you why it's the same. It's another type A. Okay, so this was 18.5. Let me just write that. This was example 18.5. And let's go on and let's do 18.6. Oops, turn the wrong page. Here we go. Example 18.6. This one says, how many liters, get myself back in line here, how many liters of a 64% glycol solution must be added to liters of a 23% to get a 42%? It's exactly the same scenario. Let me draw the picture. We have one that's too high and one that's too low. The first one is 64%. The second one is 23%. Okay, those beakers are full, and now here's our empty dish, and we need to fill this up with a 42%. Okay, I did not put any water line on this one yet because I want you to understand this dish is empty until we start pouring that in. This is exactly what a type A chemical mixture problem is set up to do. It takes one that's too high, one that's too low, and it combines them to make another one. Okay, so this is a classic type A. All right, so we're going to do the same thing. We're going to use these variables of P and D just to distinguish between the two different beakers. This is the amount that we're pouring in, measured in gallons. This is the amount we're dumping in, measured in gallons. Now we'll have some in here, right, that we filled up. Now let's see what we can find out about the number of gallons. Do we have any information? It says how many liters of a 64% glycol must be added to 77 liters to get a 42%. Okay, so this time we know that the amount here is 77 gallons. We don't know how much we have here, but we already said, oh, P, that's the number in gallons, right, that we're pouring in. So we can see that this is P plus 77. That's how much is in here. So when we set this up, we can say that, let me just point this out. The thing that's different about this problem is that we know the gallons of this amount, rather than in the first problem, we knew the gallons of the final amount, right? We don't, in the second problem, we know this one. In this one, we know this one. But let's just go ahead and use our type A diagram because that's still the best fit for this problem. I disagree with John's way of doing it, so stick with me on this. Because we have the Goldilocks, we're gonna stick with this. This we know is the measure in gallons of the amount we're putting in here. We know that D equals 77 already, don't we? So what we can see is we're not gonna need we know that D equals 77 gallons. The problem told us that. So we're not gonna need to solve for two variables. We're only gonna need to solve for this one. And then we'll be able to use that to answer the questions. Because what does John want to know? Oh, he wants to know how many liters of the 64% need to be added to this 77 to get this. So we're going to set it up the same way that we did last time. First, we're going to write a quantity statement. The amount P plus the amount D, but we know that D equals 77, so we don't have to write D. We can just write 77 equals, and now this might seem a little crazy, but the total amount is P plus 77. P plus 77 equals P plus 77. Well, that's a statement, isn't it? Now what we'll do is so this is our quantity statement. Now we'll create our value statement. Just like we always do, we will multiply by the percents. So 0.64 times P plus 0.23 times 77 equals 0.42 times P plus 77. And again, we take our first term and we multiply it by the first percent. We take our second one and multiply it by the second percent. And then here's our third one by that. So we're just multiplying the percentages by each one of the containers, really. You can think of it that way. All right. Well, I think I've got some decimals to fix, don't I? 64P plus 23 times 77 equals 42 times P plus 77. Okay. Now let's see if we can do some multiplying and some distributing. 23 times 77, let me grab this is not a piece of scrap paper. This is just an addition to my page because I want this to, I don't have extra space right now and I want to be able to solve it. So I'm going to write 77 times 23 . Okay, so there's the product of that. 1771 equals 42P, and then 77 times 42. I can already see 2 times 77 is 231, so I can just copy that. And then 4, that's 28. No, I did that wrong. 231 is 3 times 77, not the 2 times. This should be 154. And when I re-add it, see what I did? I thought I was being clever, and I took this row because that's, I thought I was, it's 2 times 77. Well, I took the wrong row though. This is 3 times 77 here. This is 2 times 77 here. So I copied the wrong part over here. Now I'm gonna re-add, and I'm gonna get 4. 5 and 8 is 3, carry the 1. 1 and 1 is 2. 3, 2, 3, 4. That's the correct answer. My bad. Plus 3, 2, 3, 4. 42 times 77. All right, let's swim some fishies. Let's get this 42P the heck over here. And 1771 is going to the right. There's my cancels. Let's see, this would be 22P. That's gone, equals, and what about this? See if I can do this without messing it up. There's a 3. That becomes a 1. There's a 6. 1463, yes, that's right. Divide both sides by 22. This is all just solving, right? There's nothing fancy or new about this. And let's, you're gonna need a calculator. No, it'll work out. 1463 divided by 22. 22 does not go into 1. 22 does not go into 14. 22 is going to go into this. What? I'm thinking 6 times 2 is 12. That's my guess. Oh, that looks like a pretty good guess, right? 6 times 22 is 132. So I'll put a 6 here. And then that's 132. Now I'm going into 143, so I'm going to take that 6 again, right? And we'll subtract 110. Oh, that should be 5 exactly, right? So here's our answer. Just a little long division there. So P equals 66.5 gallons. So now I go back to my picture, and I'm going to use the red just to help it. So this equals 66.5 gallons is our value for P. D, we already knew, right? So that means the total amount that we would have would be, let's see, what's 77 plus 66.5, 143.5 would be our total. That's how many gallons we have in all. And let's see what John wanted for our answer. He said, how many liters of a 64%? So this was the answer he wanted. There it is right there. Technically, we shouldn't use G because that's the abbreviation for grams. I use it because I don't have enough space. That's not a very good reason, to tell you the truth. John would be sad. So I'll write gal. Okay, so what was different about this problem, it was still a classic Goldilocks, and that's why we used type A. Boom, too big, too small, just right. What was different about it was that instead of being given the total, we were being given one of the amounts. That changed the algebra a little bit, because what it basically did was say, you already know what D is, so the only thing you have to solve for is P. And that made the equations look a little different. But I consider this still a type A equation because it fits that Goldilocks model. All right, let me review for you what a type B looks like. And I don't have a good problem in front of me. Let me just scan the problems and see if the problem set here. Just looking to see. I don't like John's examples. This is my best teaching on a type B. A type B is very different from a Goldilocks because what we've done is we're taking one item right here and then we're changing it in some way. We're either adding something to it or we're taking something out of it. This is the change. So I guess I'd call this a Rapunzel style because, no, not Rapunzel, Rumpelstiltskin. Rumpelstiltskin's the little dude who can spin straw into gold. That's what's happening in a type B. So this is a Rapunzel. Okay, we're changing the original item in some way and we're making it into something not completely different. I mean, we're not literally spinning straw into gold because, I mean, A, that's impossible. But we're changing it in some way. And this change is either evaporation. Do you remember doing the evaporation problems? Where we're taking out water, we're subtracting water. Or we had one where we were adding some butter fat. We had some skim milk and we were adding butter fat. So that was another example. These are the classic type A problems where we're making a change and the change will be 100%. We don't have a good example of that. So we don't need to worry about it too much. But we're starting with, for example, brine, right? Salt and water. And then we're evaporating it, which subtracts out water. And then we have a new saltier version of our brine. Like I said, I don't see a good example of those problems. Let me just look up. If you've got one in your homework that you would like to do, Luke, send me that one. And we can do it specifically. Sorry, I'm just flipping through my book. I know I'm... Here's one. It's problem 20.7. Okay, so let's do this one. In this one, we have an alloy. What we're starting with is an alloy, which means a mixture of copper and tin. Okay, an alloy means it's a mixture of copper and tin, and it is 20% copper. And I'll just use copper. I don't think that's the proper abbreviation for copper, but we'll just remember it. Now we're being asked how many pounds of copper must be added to 20 pounds of the alloy. That's what we're starting with. So we're going to add some pure copper. So this is going to be 100% copper that we're adding. Our changes can be plus or minus, and in this case it's plus. We're adding copper to get a new alloy that is 50% copper. Okay. You could see this as a type A, but to me it's a type B because we're adding one thing to the original mix to make it stronger. So this one is a little bit different. So what are we doing here? We're adding copper. And then this is the new alloy. Okay, and John wants to know how many pounds of copper must be added to get a new alloy that is 50%. Okay, so we've got all that. We know we're starting with 20%. We're gonna add, let's just call it C for the amount of copper. And then the new amount will be 20 plus C. Okay, so there's our first equation. It's a quantity equation. And we can see it's so simple because it's only got one variable in it. And we realize, just like we realized with the last problem, we're not going to need to write two equations because of the way our problem is set up. We just have one variable. So we'll take this, use a different color this time. We'll take these numbers, put this one in parentheses, and we'll multiply each one by the percents. Okay? So I'm gonna do that at the top of the next page. I'll rewrite this and then I'll write it again, multiplying each one by the percentage. 20 plus C okay, so I realize, oh, this is just going to be a single equation. I don't have to solve for 2. I know that, let's see, it's 20% times that plus 100% times C equals 50% times 20 plus C, right? 20%, 100%, 50%. That looks good, doesn't it? Okay, so again, I would like to get rid of my decimals, and I don't have to go twice. I only have to go once, don't I, to fix all of these. So it'll be 2 times 20 plus 10C equals 5 times 20 plus C. I'll distribute that in the next row. This is 40 plus 10C equals 100 plus 5C. Beautiful, beautiful. Let's swim the numbers this way and the sea fish that way. This is minus 5C minus 5C. That's gone, that's gone. 5C equals 60. C equals 12, and I know it's going to be gallons. Let's go see if that makes sense. So what that tells, oh, it's not gallons, I'm sorry, I'm still in the other land. It's pounds. Okay, so equals, what did I get? 12? Yes. 12 pounds. So we started with 20 pounds of this alloy, and according to my calculations, we added 12 more pounds of just copper, and now our new alloy, we will have 32 pounds. And these are all pounds. I should write that in. LBS. And let me fix it back here because this is just bothering me. Right? And that makes sense. Certain amount of sense, right? 20 plus 12 would give us the new amount. And I'm just flipping to the back to check the answer. 12 pounds. That's the right answer. Beautiful. Okay, so I'll say it one more time. My takeaway for you is that the type B works best when we are introducing a change to our original situation that involves changing one part of the original combination 100%. We're either evaporating, which means taking out 100% water, or we were adding butterfat. There's a famous problem from Algebra 2 that does that. This one, we had an alloy of copper and tin, and then we were just adding more copper, so it was 100% copper. And then that got us the new combination. This is, to me, the classic type 2. Something is being changed. Type 1, as I've said, is our Goldilocks friend because we're just using different strengths of the same chemical to find the one in the middle that's just right. Okay, I hope that helps. What I'm noticing is that John is using almost all this style of problem in this level, the green book. Last year he had more problems that were very specifically the type B changes. Now, a lot of them fit this mode. So let me know if it's still confusing to you. I hope that helps. and then I will discuss the other, I'll answer your other questions in different videos, but that's enough to torture you for today. Okay, thank you. Goodbye.